Hi, my name is Daniel Rosendo. I'm a PhD student from INRIA, France. Today, I will present E2Clab. E2Clab is a framework that implements a methodology designed to support reproducible experiments and also to deploy applications in the context of the computing continuum on large-scale testbeds. This work is a collaboration with Pedro Silva, a postdoc researcher at University of Potsdam, and also Mathieu Simonin, an INRIA engineer. The Computing Continuum refers to a digital infrastructure jointly used by complex application workflows that generates data from IoT Edge devices to the HPC Cloud data center. This new emerging paradigm brings new research challenges and opportunities, and researchers, after proposing the novel approaches and solutions, they aim to deploy the real-life applications on large-scale testbeds to conduct some experiments. After the researchers have proposed their own solutions, the next research step consists in evaluating and validating the proposed approach. And here, two crucial aspects are important during this phase. They are achieving representative setup to understand the performance of the application and also establish procedures for reproducibility. Regarding reproducibility, the Nature published a survey, and they discovered that more than 70% of the researchers failed to reproduce another scientific experiments, and also more than 50% of them failed to reproduce their own experiments. So, in order to successfully accomplish those two crucial aspects, researchers face two new technical challenges, since achieving representative setup to understand the performance requires the installation and configuration of many services and parts of the applications in the computing continuum. It also requires the configuration of the network, the mapping between application parts with the underlying infrastructure, defining the execution workflow, and also following well-established procedures for reproducibility. As this is a challenging step, if researchers fail to accomplish them, they end up with a simplified testbed setups that presents many abstractions, scalability issues, and due to the lack of information about the experiments, those experiments are hard to reproduce. So, what would be an ideal solution? An ideal solution would be one that abstracts all of those complexities for the experiments, allowing them to focus on the high-level aspects of the experiments. And the idea is that they can achieve a representative testbed setup that is easy to scale and also leverage reproducible experiments. In the literature, we have some existing solutions that maps complex application workflows in distributed resources like the Pegasus framework. But it's important to highlight that in this work, our focus is on the deployment of applications in the context of the computing continuum on large-scale testbeds, and also to support reproducible experiments. Based on those challenges, we have proposed E2Clab. E2Clab is a framework that allows one to deploy real-life application workflows on representative settings of the physical infrastructure underlying this application, in order to accurately reproduce the relevant behaviors and understand the performance. In order to achieve that, E2Clab provides pre-configuration files to define the experimental environment. Those files were designed to be easy to use and understand, and through them, experimenters can reproduce the scenario characteristics in a descriptive manner. So, E2Clab managers interpret those configuration files and enforce those configurations on the physical testbed using the ENUSLib library. In E2Clab, achieving a representative setup to understand the performance means to rigorously mapping the scenario characteristics to the physical testbed, identify and control the configuration parameters of applications and services, and also identify the relevant performance metrics. E2Clab also supports reproducibility, so it provides a well-defined experimental methodology. It also provides access to the experiment artifacts and access to the experiment results. The methodology implemented in E2Clab was designed to support reproducible experiments, allow the map between application parts and the physical testbed, allow the experiment variation and the transparent scaling of the scenario, provide network emulation in order to define network constraints in the Edge to Cloud Computing Continuum, and also provide experiment management features like the deployment, execution, and monitoring of the resources. This methodology consists in three processes. The first one consists in providing access to the artifacts, then defining the experimental environment, and lastly, providing access to the results. Regarding the first process, provide access to the artifacts means that all the artifacts used in the experiment should be available, and it consists in the dataset, the software, the algorithms, and the configuration files. After that, the next step consists in defining the experimental environment, and we divided this process in three sub-processes. They are define layers and surfaces, define network, and define workflow. Regarding the first one, as you may note, this methodology is centered in the concept of layers and surfaces. Surfaces represent any component in the scenario that provides a specific functionality. In the context of the computing continuum, surfaces may refer to data producers, ingestion systems, or processing engines. Layers can be used to group those surfaces and also define a hierarchy between them. Those layers can also be used to represent the geographical distribution of those surfaces in the scenario. In the context of the computing continuum, those layers may refer to the edge, fog, and the cloud. After that, the next step consists in defining the communication constraints between those layers and surfaces. And for example, a user may define a 5G network between the IoT Edge devices and a fog gateway. Lastly, the next step consists in defining the workflow, that means the execution logic and the interconnection between those surfaces and layers. So for example, the user may define that a set of IoT Edge devices should be connected to a specific gateway on the fog layer. After defining the experimental environment, the last step consists in providing access to the results. So all the files generated during the execution of the experiments, like log files, metric files, monitoring data, that means everything that was used to analyze the experiments, should be provided also in a public repository. How can you use E2Clab? In this presentation, I will be considering a smart surveillance system, but actually, you can use E2Clab to analyze your own IoT application or to deploy your edge environments. So, supposing that you have developed this application, and this application relies in the edge, fog, and the cloud infrastructure, and we have data producers at the edge, gateways on the fog, and some ingestion systems and processing frameworks on the cloud side. Besides that, in this application, we are considering two kinds of processing. The hybrid processing, where the processing is split in two places. On the fog, so here we have active gateways doing some image processing, and also on the cloud, where it is used to aggregate the results sent by gateways. The second processing approach consists in the cloud-centric. In this configuration, all the processing happens on the cloud side. So, after you have developed this application, you want to understand the performance of both processing approaches. So, in order to choose between them, you have defined the following research questions. What is the impact of the network on the end-to-end latency? How workload scalability impacts on fog gateway performance? and what is the impact of the hybrid processing on resource consumption. So, on the next slides, I will show you how HPC helps you to answer to those questions and to choose between both processing approaches. So, the first step consists in expressing the scenario characteristics using the three configuration files. So, in the first file, the users define the edge, fog, and cloud layers, and some services like Flink, Kafka, gateways, and etc. Then he defines some network constraints by defining the delay, loss, and rate. And lastly, in the workflow configuration file, he defined the execution logic and some interconnections between the services. After HPC interprets those configurations and enforces on the physical testbed, the user ends up with the following configuration. Here we used 35 physical machines on grid 5000, so we end up with 640 cameras, 16 gateways, a Kafka cluster, a Flink cluster, and an application to collect some metrics in the scenario. In order to answer the first versus question, what is the impact of the network on the end-to-end latency? The user takes advantage of the transparent scaling provided by HPC to scale between small, medium, and large workloads, and also to emulate three network profiles. So, on the first graph, we have fixed the network configuration and scaled the scenario between small, medium, and large, while in the second graph, we fixed the workload, we used a large workload, and we varied between the network profiles. After executing the experiments, the experimenter observed that cloud-centric processing presented higher latencies even when we scale between small, medium, and large workloads. And on the second graph, lower latencies were obtained with an end-to-end link of 1 GB. To answer the second precise question, how workload scalability impacts on fault gateway performance. Again, the transparent scaling theory was used by the user to scale between 20, 30, and 40 cameras per gateway to emulate one network profile and also to monitor resource consumption of gateways like CPU and memory. After executing the experiments, he observes that more messages are sent by the passive gateways, since the active ones aggregate some messages. Then, regarding memory usage, with 20 cameras, active gateways consumed 45% more than the passive ones, and with 40 cameras, both consumed around 16 GB. Lastly, regarding CPU usage, active gateways consumed twice as much compared to the passive ones, since the active gateways die some image processing on fog devices. Lastly, to answer the third versus question, what is the impact of hybrid processing on resource consumption? Again, it takes advantage of the transparent scaling to scale between small, medium, and large workloads, emulate one network profile, and also monitor resource consumption like the memory of Flink and Kafka. In the first graph, we can see that for large workloads, aggregating and processing these data volumes in the cloud can translate into reduced resource costs, since hybrid processing sends less data to the cloud side compared to the cloud-centric approach. Next, regarding the Kafka and the Flink, they consumed less memory in the hybrid approach. And in the third graph, we can see that Flink uses 6 GB for hybrid processing against 15.5 GB for cloud-centric. So, we have demonstrated how HPC helps you to understand the performance of the applications and how the hybrid processing approach and the cloud-centric one performs on the X scenario. Besides that, we also like to highlight that thanks to the features provided by HPC, the user could easily configure a Flink cluster and a Kafka cluster, deploy 16 gateways and 640 cameras and interconnect them in round robin, define the network constraints between the edge, fog, and cloud, manage, validate, and backup the experiments, and also analyze the scenario end-to-end, considering the edge, fog, and the cloud layers, but also focus the analysis in a specific layer of the scenario, like in the fog gateways. So, can you imagine the effort and time saved to define and deploy all of those configurations in a real-life large-scale testbed? Besides that, with E2Clab, you can improve research quality aspects of your work, like reproducible experiments. So, all of the artifacts and results used in this presentation can be found in our repository. As future work, we plan to extend E2Clab in different domains. The first one consists in building support for other large-scale experimental testbeds like Chameleon. We also plan to leverage E2Clab to build a benchmark suite for applications running on the Computing Continuum, evolve E2Clab towards an emulation framework for applications in the Edge-to-Cloud Computing Continuum to emulate common behaviors such as resource-constrained devices, failures of network, services, and etc., and also to emulate mobility of edge devices. Lastly, we also plan to deploy more real-life use cases using E2Clab to perform large-scale experiments. You can also help us to improve E2Clab, so provide feedback of your use cases and the new feature that you would like to see implemented in E2Clab. If you want to know more about E2Clab, you can access the documentation webpage. Thanks for your attention.